So this is some notes for section 1.5 in the David Lippman book, and this is a set of cliff notes, if you want, that somebody shared with me at one time. I think it's pretty useful. It's the same material that's in the textbook. So maybe this little shortcut will help save you some time. Okay, so when I generally work with transformations, I usually work inside out. So that's why you're going to see with these descriptions that I wrote is that, notice it's shifted left 2. Remember, this is minus a minus, so it's plus. So shifted left 2. I worked inside, and then I talked about the vertical stretch. Then I talked about the shifted up and down. Now, will I always work with that? Sometimes it's easier not to, but generally this keeps me from getting in trouble if I work inside out, especially when it comes to graphing. Sometimes with these canned functions, they're just the transformed toolkit functions. It doesn't really matter. When you get down to something like number 3, well, then it matters a little bit more, and you'll see, because we don't know what the function is. We just got to deal with the behavior. But for this one, I certainly see here. What do I see? I see a parabola with a vertex. I haven't done parabolas per se in this course, but I'm sure you've worked with them earlier. So I know parabolas look like this, or they could open down, and they have a vertex right there, and that's what we're going to deal with. So I see that vertex, instead of happening at 0, 0, is going to shift left 2, then down 4. And see, and that's okay. It's kind of in a little bit different order than the way I wrote it, but because we know the basic shape, that's okay. And then I see that it's stretched vertically by a factor of 3. Now, normally, normal everyday parabolas usually act like this. You go over 1, up 1. Because think about x squared. If x equals 1, then x squared also equals 1. And if x equals -1, y also equals 1. So it goes like this, and then it goes over 2, and if I square 2, it's going to go to 4, so it goes up 4, and goes over left 2, and goes up 4, and it goes go over 3, and up 9. I don't know if I have enough space in this graph. 1, 2, 3. Oh, I do. Barely. So that's what the normal, that is what the equation, or that's what the graph of y equals 1 times x plus 2 squared minus 4 would look like. And this has that extra 3 in front of it. So that means it's being stretched vertically. So instead of going over 1, up 1, it's going to go over 1 and up 3, because it's getting multiplied by that 3. See that? And then go left 1, it's going to go up to 3. And then it goes over 2, and instead of going up 4, it's going to go up 12. And of course, I'm off my graph. But that's what that's going to actually look like. So that green graph is actually the graph of this function. Okay, so I hope you could plot points. I did plot points in a way, but I didn't really make a table. I kind of understood how it worked. If this had been 1/2 x plus 2 squared minus 4, then that would have gone over here. Let me get a different, what color do I have? Yellow. That would have gone over 1, up 1/2, which is kind of hard to graph. So I would have gone over 2 and only up 2, because it's supposed to be going up 4, but it's only climbing half as fast, right? So then over 3 would be up 9, but actually it's only going to go up 4.5. 1, 2, 3, 4.5, and right there. And then I'm kind of out of space on the left. So you see how that opens up wider. It's a wider graph, and of course we knew it was going to be a wider graph because of that vertical compression. Okay. The other thing to keep in mind, that a vertical compression is the same as a horizontal stretch. Okay, you can write them both ways, and sometimes it's easier to deal with it as a horizontal stretch or compression. Sometimes it's easier to just make it a vertical. This next one I do won't work. Let me work through whatever these canned ones, and then I'll add a couple. So for this square root function, I see a couple of things, and a couple that are really different. Where's my pointer? Well, that's the right shifted 3, so that's easy. And This -2 is kind of weird. The negative in particular is weird because that does that reflection around the y-axis or around the vertical axis. I wrote this as vertical axis because this is actually getting shifted to the right 3. So the axis it's going to reflect around is x equals 3, but it's the vertical axis, and that doesn't matter. So how would I graph this? I would do it this way. I know square root graphs typically look like this: over 1, up 1, because the square root of 1. Go over 4, it's only going to go up 2. So I know that's the everyday square root of x. So what's happening here? Well, I know it's getting shifted to the right 3. So here, let me get it ready and going. So it's right 3. But then it's got some things happening to it. Instead of going over 1, up 1, it's acting like if you just think about this. If I think about the square root of 2x, if I went to here, I'm going to do this down here. The square root of 2x, that would look like this. If I went over 1, it would be acting like the square root of 2, because 2 times 1. If I went over 2, it would be acting like the square root of 4, which is 2. So do you see how it's been compressed? See, if we went up here, see how it's growing faster? So the horizontal stretch or compression, because it's compressed, it's growing faster, is the same thing as the vertical stretch. So, I mean, we could write this way. You could write this as the square root of 2 times the square root of x, but that's a little obtuse. If it had been the square root of 4x, well, that's growing 4 times as fast. So it's a horizontal compression by a factor of 1/4. But that's the same thing as an exponential, vertical stretch by a factor of 2, because the square root of 4 is 2. So we could pull it out and treat it this way. My open math is going to expect they're going to ask you, what's the horizontal stretch? Well, you're going to have to deal with the horizontal. But in reality, you could rewrite these all as verticals. And to me, verticals are much easier to deal with. But getting it right is the important part. So whether I call it a half a dozen or 6 eggs, it doesn't matter. So here, let me stop this video and I'll clear this up a little bit. Okay, so let's see, this is recording, right? Yep, okay. So we've got a square root function that's been shifted, and it's from the origin, been shifted right 3. It's going up 1 because of the +1. So let's do that. And then instead of heading over here to 2, well, it's not 2, but coming over 2 up 2, because remember, I'm treating this like 2x. So instead of square root of 4, I'm going to come to the left and do that. And then I want another nice lattice point. And yes, while the square root of 9 would be the next point, I guess I could do that. That means coming over 4.5, right? So 1, 2, 3, 4.5. So that'll be about the next point. The next point would be, I'd love to have the square root of 16. Well, since I'm doubling it, it has to be 8. If I come over 8, I think it's here. So that's that point. So there is that graph of that function. Notice I make my lines kind of fat because that covers up shaking hands, and I can kind of add a little curvature to it. I guess I could do a little erasing too. Well, anyways, that general idea is what we're looking for, domain and range. Okay, this next one now, let's see here, is a little different. This isn't a toolkit function. So when we aren't given toolkit functions, what we need to do is, what we're going to do is just look at points and then connect them. Because what's nice about it is, like, this graph has that point and that point and that point, and they're just connected by lines. So we'll just focus on the points and then connect the lines. So what am I seeing here? So I'm seeing that the points are getting stretched by 3, right? And because this isn't moving left or right, I can't go moving. I gotta leave the function in the same place. but I got to do some stretching to it, some horizontal stretching. So I'm going to treat this point that's like a vertex. I'm going to treat that like a stationary point. I also know when I'm done that this graph has to open up like this, okay? And it's got to be stretched out more. So let's see here. So let's concentrate on this point right here. So I know that has to get moved away 3 times. Right now, this is 2 times, 2 places away, so it'll have to be 6 places away when I'm done. So if we move this over 6, so 4 more spaces, right? 1, 2, 3, 4, and then, so that's we took care of the horizontal stretch. I'm going to deal with the shift up. So I know next it should get shifted up, and then it's going to get reflected around the x-axis. Okay. I think that looks good. And this next one, now we're going to treat that as the vertex. So I'm not going to move that left or right. I'm just going to do this, and I really can't do this any kind of stretch with it. So I'm just going to worry about moving it up and then reflecting it. So it goes up 1 and then down. Let's see, that's what, 4 lines up. So 4 lines down. Now this one we're going to move. It's 1 space away from that midline. So we're going to make it 3 times that distance. Move it up 1. Then reflect it. Now I think that graph looks like a function that's been reflected around the x-axis and then stretched horizontally 3 places. Okay, it's certainly 3 times as wide there, and it's 3 times as wide there. It's been reflected. So I think that's it. So I hope that helps. We can always do some more of these. There's plenty in the textbook and the paper exercises, and there's a couple of them in my open math. I'm going to ask you something like this on the first exam, okay? So you want to make sure you get some practice with it. So we've got another toolkit function, another absolute value function, so it's not too bad. We know normally absolute value functions start at the origin, and then they have a slope of 1 and -1 because you just take the x value and make it positive, right? It's already positive, so it's like the line y equals -x and like the line y equals +x put together, but they stop, you make a piecewise. So maybe while I'm thinking about this, because this will help you in calculus, if I want to write at y equals absolute value of x as a piecewise defined function, we'll do this. We'll say it looks like -x from -infinity until 0, and we'll keep it closed there. And then it looks like +x on 0 to infinity. Notice I did the open thing at 0. And so that's how you can break an absolute value function up into 2 linear functions, then do whatever with them. Okay? That's another side. I digress, as they say. So I see a function that's been shifted right 1 up 2. So I'm going to go absolute value of x -1 plus 2, and then I see a vertical compression. Now normally these things go up by 1, by 2, right? And it's only going up, it's supposed to be over here up at over 2 up 2, but it's going over 2 up 1. So that's a vertical compression of 1/2. Now we could put this inside, and if you want to deal with it as a horizontal, let's see, that would be a horizontal stretch. We'd put it inside the function and would say 1/2, and you'd need to put a parenthesis x -1 plus 2. I think that's starting to look a lot more complicated. That vertical is definitely easier in this case. Okay, so that's kind of what you're going to do. I would recommend you do some of the paper exercises out of the book. If you the answers you're out at the David Lippin textbook site. I probably have them somewhere on my dlma.net site too. But so I guess this is probably a long enough video. Go get her done.